Oh, hi. I'd like to spend a few minutes talking about the mole and making some calculations involving moles. I put a problem up here on the board. The problem reads that a student obtains, you can think of this volume and mass of water as being maybe like a test tube full of water. It's a little bit more than half an ounce worth of water. And I picked this number on purpose. Yes, it looks like it's an obscure number, 18.015 grams of water, but it'll turn out to be very, very helpful. So a student obtains a little more than half an ounce of water, 18.01 grams. Well, using 6.022 times 10 to the 23rd, or Avogadro's number, very powerful tool, we can calculate eventually how many molecules of water molecules, H2O, very, very small though, can't see them, how many are present in the test tube. So a very incredible tool that we could just use a very primitive balance, pour some water in, measure out 18.015 grams or any other amount, and determine how many water molecules are present. You could even determine how many oxygen and hydrogen atoms are present inside there. So we're going to develop this idea called a mole. 1 dozen is 12. A mole, 1 mole, is equal to 6.022 times 10 to the 23rd, and that is a very, very large number. If you had this many Coke cans, 12-ounce soda cans, it would cover the entire face of the earth 100 miles high. Cover the entire earth with Coke cans and have to stack them 100 miles high. That's like unfathomable. Take a long time to do that. It's absolutely a huge number. So, part A of this problem has us take our grams and change it into moles. I'm going to write down what we know, 18.015 grams of H2O, and we're going to need a conversion factor to change this into moles of water. That conversion factor ends up coming from the periodic table of the elements. We need to put together the conversion factor a little bit because the periodic table has just this, elements, and this is a molecule. According to the periodic table of the elements, oxygen has a mass of 15.9994. It's written on the entry for oxygen. Now the entry for oxygen does not list the units. It would be redundant to put these units on the periodic table 116 times, but the units are in fact grams per mole. What I'd like to do for this first exercise is not write grams over moles. I would like to set this up so it looks like a conversion factor. 15.09994 grams, almost 16 grams, over, let me extend that line out, 1 mole. I'll abbreviate the grams over moles in a couple of moments. That's for the oxygen. The hydrogen is 1.0079, and I can use this little compound set of units there and call it grams per mole. I don't need to do this every single time, but I want you to see that we have a numerator and a denominator. We have ourselves a conversion factor. Now there's 2 hydrogens, so one of the hydrogens has a mass of 1 gram per mole plus the other hydrogen. When we add these up, 16, 1 and 1 with the change, we end up having a mass of 18.015 grams per mole for water. 16 and 1 make the 18 and the change. Well, now you can see why I selected a problem where the student weighed out 18.015 grams. That's our conversion factor. It has the units of grams per mole. Instead of putting the 18 in here somewhere, let me put the correct units. We're speaking of water, so I put water in here, completely optional. You can just put grams per mole. We know that the problem involves water. Grams go on the bottom so that the grams will cancel. Moles go on the top. We're converting grams to moles, and we need moles to appear. Conversion factor says 18.015 grams. 18.015 grams. Yes, it goes on the bottom. Yes, we divide, but I wasn't really thinking about that. I was letting my units do the work. Grams per mole, 1 mole. No need for a calculator. We have ourselves to 5 significant figures, 1 mole of water present. Part B of this problem asks us how many water molecules are present. And now we're going to use the idea of mole, 1 mole being a count, 6.022 times 10 to the 23rd of something. By the way, yes, chemists often are called geeks, and it's true. We actually celebrate Mole Day, and it's October 23rd. Mole Day is October 23rd, 1023, so party hardy, Mole Day. Let me work on part B of this problem. From part A, we know we have 1.0000 moles of water, and we're going to convert that into water molecules. 6.022 times 10 to the 23rd is a count. It's often called Avogadro's number. I'm not going to make a note if I'm going to put that 6.022 times 10 to the 23rd on the top or the bottom. I'm going to let my units do the work. We need moles to cancel. I'm going to write moles on the bottom, and I'm not going to put water in here. We know we're speaking of water, so the moles will cancel. And we need molecules to appear. Let me put in molecules. 1 mole, according to the conversion factor, so 1 and the mole do not get separated, is equal to 6.022 times 10 to the 23rd, and in this case, molecules. So we have ourselves 6.022 times 10 to the 23rd water molecules. Let me make a little note for you, and that is, if the student weighed out twice the mass, 36 grams, they would have 2 moles of water present, and we would take Avogadro's number through this. We would end up with 1.2044, or twice this much, times 10 to the 24th water molecules. So it's completely proportional. If we started with 10 times the mass, we would have 10 times the moles, 10, and we would have 10 times the water molecules, 6.022 times 10 to the 24th. So it's all proportional. Let me ask you to do a little exercise here. You can check the answer on the worksheets for week number 4, and that is, take this value for the water molecules and calculate how many oxygen atoms are inside this sample and how many hydrogen atoms. And if you need a hint, stay tuned. Each water molecule has 1 single oxygen, denoted by the red sphere in the middle, and a couple of hydrogens. So if you're going to ask yourself how many oxygen atoms are in this sample, this is how many oxygen atoms are in the sample. Each molecule has 1 oxygen atom. If you're going to ask yourself how many hydrogen atoms, it's this number for the molecules. You're going to multiply that by 2, because each one of these molecules has 2 hydrogens.